Welles ordinary least square method to estimate two unknown parameters, that is alpha and beta. In the Welles method, the sum of the square error, that is EI, must be minimum. We know from the sample regression function it's denoted by, this is estimated, y hat is equal to alpha hat plus beta hat xi. Here y hat is estimated and two parameter alpha and beta hat are two estimated parameter, and yi is actual and yi hat is estimated. Here error, that means E, equal to actual minus estimated. So EI is equal to yi minus yi hat, and sum of this error term, that is EI square, is equal to yi minus yi hat whole square, and EI, sum of EI, it's denoted by S, is equal to summation yi minus yi hat whole square. This EI square, that is sum of the squared error, must be minimum, and first order condition will be 0 and second order condition will be positive. So first yi, that is same yi, but yi hat is equal to alpha hat plus beta hat xi. So S is equal to summation yi minus alpha hat minus beta hat xi whole square, taking derivative with respect to alpha and beta and getting the value. S is equal to summation del S by del alpha is equal to 2 yi minus alpha hat minus beta hat xi minus 1. That means we are taking derivative with respect to alpha hat, so there is a negative sign, that is why minus 1 is equal to 0, first order condition. So yi is equal to ultimately alpha hat plus beta hat xi, and taking sum to the both side and getting that summation I equal to 1 to n is equal to summation I equal to 1 to n alpha plus beta summation I equal to 1 to n xi. S is equal to, already know that yi minus alpha hat minus beta hat xi square, taking derivative with respect to beta and getting the value is equal to 2 yi minus beta hat plus beta hat xi into minus xi for this term, and is equal to 0. There is a first order condition, and ultimately we are getting from the previous solution that summation yi, when we are taking derivative with respect to alpha, that is why we get summation yi is equal to alpha hat plus beta hat xi, and when taking derivative with respect to beta hat we are getting summation yi xi is equal to alpha hat summation xi plus beta hat summation xi square, and we represent it as a matrix form and getting this yi xi is equal to, this is equal to sign in matrix n xi 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 square into alpha hat beta hat bit. We are solving this matrix and getting the value summation xi yi by summation xi square. So we know small xi is equal to capital Xi minus x bar, and small yi is equal to yi minus y bar. Small xi small yi, it's coming from sample, and ultimately sum of yi it's divided by n. Sum of alpha hat is divided by n. Sum of alpha hat means n number of alpha hat is divided by n, and beta hat summation xi is divided by n. And finally we get y hat. We know that yi minus n is equal to y bar. This is average, total minus number of observation, its mean, that is y bar is equal to alpha hat plus beta hat x bar. So alpha hat, if you interchange the values and get alpha hat values is equal to y bar minus beta hat x bar. Before going to the blue property, we will check the values of wi. We know that the summation wi is equal to 0. We prove that how to get summation wi is equal to 0. And next, summation wi xi is equal to 1, already proved this value. And summation wi square is equal to 1 by summation xi square, that is also proved here. And beta hat, we know this is the deviation from small xi into small yi divided by summation of small xi square. It's equal to wi yi, because yi is already there in the equation in the deviation form. And summation xi by summation xi square, that is equal to summation wi, that is why we are taking this term summation wi yi. So beta hat is equal to summation wi yi. And now prove beta hat is linear in y. So here beta hat is linear with y. Beta hat, we know that the beta hat is equal to summation wi yi is equal to summation wi yi means yi. Here we use small yi. Small yi, it's multiplied, that is yi minus y bar. So summation wi yi is minus summation wi y bar. We know that summation wi is equal to 0, but ultimately beta hat is linear with yi, that is summation wi yi. And beta hat is equal to w1 y1 plus w2 y2 plus w3 y3 plus wn yn. Here I equal to 1 to n. And second is beta hat is linear with ui. So similarly beta hat is equal to summation wi yi, here wi, and putting the value of yi, y, that is capital yi. So yi equal to alpha plus beta xi plus ui, multiply all these terms with summation wi. So we are getting alpha into summation wi plus beta into summation wi xi plus summation wi ui. So we know that the sum of wi value is equal to 0 plus beta into 1, that means summation wi xi is equal to 1. And we are getting the term, other term is summation wi ui. Here beta hat is equal to beta plus summation wi ui, or beta hat minus beta is equal to summation wi ui. So beta hat is linear in ui. And other, we prove that beta hat is unbiased, that means expected value of beta hat is equal to beta. We know that the beta hat is equal to beta plus sum of wi ui. So from here beta hat is equal to beta plus expected value of beta hat is equal to beta plus expected value of wi ui, sum of wi ui, and we can write in such a way that expected value of beta hat is equal to beta plus wi, putting inside and taking expectation of ui, because ui is a random random part. Ui is the random part, that is why taking expectation. So expected value of beta hat is equal to beta plus wi, expected value of ui plus w2 expected value of u2 up to wn expected value of un. But expected value of beta hat is equal to beta because expectation, taking expectation of ui is equal to 0. So unbiased proof, beta hat, expected value of beta hat is unbiased, that is already proof. And we will now prove the variance of beta hat. So variance of beta hat is equal to expected value of beta hat minus expected value of beta hat whole square. Here we get expected value of beta hat minus beta, because we know that expected value of beta hat is equal to beta. So variance of beta hat is equal to some expected value of sum of wi ui, because we know that the beta hat minus beta is equal to sum of wi ui. So here we put this value and getting expected value of summation wi ui whole square, expected value of sum. So if we divide this I, then we get expected value of w square u square plus w2 square u2 square, w3 square u3 square, w4 square u4 square, wn square un square, plus the other cross multiplier, that is 2 into summation double summation I is equal to 1 to n, j is equal to 1 to n, but I not equal to j, expected value of ui uj and wi wj. We taking expectation of ui uj, that is 0, that is equal to 0. So taking the term w1 square and expectation on the random part, that is expected value of u1 square, similarly plus taking w2 square and expectation of u2 square, taking in outside w3 square and um, taking expectation of w3 square, plus and finally we get wn square uh, into expectation of un square plus 0, because we know the expected value of ui uj is equal to 0. So the cross product is equal to 0 and there is no autocorrelation, that is the expected value of ui uj is equal to 0. And finally we get w1 square into sigma u square, w2 square into sigma u square, plus up to wn square into sigma n sigma u square. So sigma expected value of u1, expected value of u2 square, expected value of u3 square, expected value un square is equal to sigma u square. There is the property of homoscedasticity. So ultimately we are getting the value, expected value, sorry, wi square sigma u square into wi square or wi square. We know that sum of wi square is equal to 1 by summation xi. So variance of beta hat is equal to sigma u square by sum of xi square. Now we come to the other part, that is we are taking other estimator to compare with beta hat, that is beta hat minimum variance or is beta hat satisfy blue property or not. That is why we take another estimator, beta tilde. Beta tilde is equal to ci summation ci yi ci is equal to wi plus di and yi equal to alpha plus beta xi plus uy. Here already putting the value summation ci into alpha plus beta xi plus uy and multiply alpha is summation ci plus beta summation ci xi plus ci ui. Here ci is wi plus di. So putting all this value here, alpha into summation widi plus beta into summation widi into xi plus summation widi into ui, and beta tilde is equal to alpha summation wi plus alpha summation di plus beta summation wixi plus beta summation widi plus beta plus wiui plus diui. Here we know summation wi is equal to 0, summation di is equal to 0, but summation wix equal to 1 and summation xi di equal to 0, and all the other terms will stay. That is why alpha into 0 plus alpha into 0 beta into 1 plus beta into 0 plus summation wiui plus diui. We know sum of wi is equal to 0, sum of di is equal to 0, sum of xi wi is equal to 1 and sum of di xi is equal to 0. That is why beta tilde is equal to beta plus summation wiui plus w diui. So taking expectation both side and getting expected value of beta tilde is equal to beta plus expected value of w1 u1 plus w2 u2 plus w3 u3 plus up to wn un plus expected value of d1 u1 plus d2 u2 plus d3 u3 plus up to dn un is equal to beta plus taking wi into expected value of ui, w2 expected value of u2, w3 expected value of u3. Similarly di expected value of ui, d2 expected value of u2, d3 expected value of u3 and dn expected value of un. Here expected value of beta tilde is equal to beta because we know that the expectation of the random part is equal to 0. That means expected value of ui is equal to 0. Finally we get the value expected value expectation of beta tilde is equal to beta. And so this is beta tilde is unbiased estimator, but what will be the variant that we'll need to check. We know that beta tilde equal to summation ciyi. Here not put the value ci, but in the first stage put the value of yi is equal to alpha plus beta xi plus ui. So multiply with summation c is equal to summation alpha into summation ci beta into summation ci xi plus summation ci ui. So putting the value of ci and ultimately getting alpha summation widi plus beta summation widi into xi plus summation ci ui. So ultimately getting the value uh, summation wi plus some alpha summation di plus beta summation dixi plus beta summation wixi plus ciui. But we know that wi is equal to 0, summation di is equal to 0, summation wixi equal to 1, summation wxi di equal to 0, and get the value will remain same summation ciui. So ultimately get beta tilde is equal to beta plus summation ci ui, and beta tilde minus beta is equal to ciui. So here now we try to find the variance of beta tilde is equal to expected value of beta tilde minus expected value of beta tilde whole square. Expected value beta tilde minus beta, because we know beta tilde expected value beta tilde equal to beta, and in the previous step we get that the beta tilde minus beta equal to summation ciui. So expected value of ciui whole square and ciui. So ci means expected value of sum of wi di into ui whole square. So multiply summation wi ui plus summation diui whole square. Expectation it's outside, so expected value of summation w1 d1 whole square u1 square plus sum of w2 plus d2 whole square into u2. Similarly, wn plus summation dn into un square, and the cross product summation double summation I equal to 1 to n j equal to 1 to n I not equal to j expected value of ui uj, mm, uh, wi plus di into wj plus dj into ui uj. So expected value here I am looking a mistake, that is this plus will, so this plus sign will not be there, that is basically a multiplication sign. So w1 d1 square expected value of u1 square plus w2 d2 square expected value u2 square plus wn plus dn square expected value of un square plus double summation expected value of ui uj into w1 d1 into w2 d2, and finally putting the value expected value of un square equal to sigma u square summation w1 d1 similarly up to nth term, and last term is equal to 0, and finally getting variance of beta delta equal to sigma u square, summation wi di square. So we can conclude that beta hat its minimum than beta tilde. So beta hat has a minimum variance.